Good morning, dear colleagues. Let me first acknowledge the organizing committee, Professor Radu, Professor Mafte, for their kind invitation and also to organize this conference despite global pandemic. The title of our presentation this morning is Cyber Physical Systems, Advanced Nanomaterial-Based Unmanned Aerial Platform for Real-Time Infrastructure Integrity Monitoring. By way of introduction, I'm Ashok VASEASHTA with the International Clean Water Institute and few other affiliations which are shown in this slide. As you know, that we live in a highly connected world. Even using our iPhone, we can control several different aspects of our life, such as communication, such as transaction, such as devices, as are shown in this slide. So based on that, what I would like to present to you today is using cyber physical system, their concepts and application, how we can connect systems worldwide for civil engineering types of application. So I want to take you through a brief history of our project, as we have been involved with this project for quite some time without actually knowing that we were looking into smart and connected world. So I'm going to also show you some of the recent applications, how they integrate into this project, and of course enhance the capability, look at some ground capabilities, and look at some new and upcoming platform for structural integrity monitoring, some of the potential application path forward, and the next steps. So I want to introduce the concept of cyber physical systems, which is essentially a multidisciplinary engineering discipline. As a matter of fact, I teach courses in cyber physical system. And this is focused on technology with a strong foundation in a mathematical abstraction. Cyber physical system integrates the dynamics of the physical processes with the software and networking, providing abstraction and modeling, design, and analysis techniques. This is a domain that consists of integrated and networked system of systems with physical processes that are controlled or monitored by computer-based algorithms. And of course, it has lots of capabilities, but nonetheless, it has challenges because we are conjoining abstractions that have evolved over centuries for modeling processes with abstraction that have evolved over decades in computer science. So essentially, we are conjoining digital platform with the physical aspect. So it makes somewhat challenging. But nonetheless, it has lots of useful application, as we will see in the following slides. So this is a schematic of the cyber physical system and the mission space per se, where we have cyber, where we have physical spaces having feedback space, application space, and scalability. So the advances in cyber physical system have significant applications in terms of capability, scalability, resilience, safety, security, flexibility, and conformity to systems within a domain of interest. Because of its economic and societal potential implication of such systems, there is a great potential to be realized going forward. So in terms of smart and connected communities vision, the communities around the world are entering a new era of transformation in which residents and their surrounding environment are increasingly connected through rapidly changing intelligent technologies. And we want to tap into this technology for some of the new platform and for this conference with applications which relate to civil engineering, such as structural integrity monitoring. And that's what I would like to show you today by way of some examples. Since area of my research is on nanomaterial, I want to also use advanced nanomaterial based platform which are integrated with these cyber physical systems for economic opportunity, prosperity, growth, safety and security, health and wellness, and to improve overall quality of. So some of the funding agencies, ranging from National Science Foundation to European Union, now Horizon Europe, they have in their vision to fund several activities to address global challenges and, of course, enhance the European competitiveness. And smart and connected communities is one of the platforms which they want to enhance going forward. So this slide shows some of the methods which are used for structural integrity monitoring and risk assessment, and they consist of visual inspection, stress strain, acoustic emission monitoring, structural vibration, embedded system networks, PCT-based ultrasonic guides, environmental parameters, fatigue, in conjunction with different types of computational platform to understand different types of complexities in the in the structures. So the next, what I would like to do is to take you through a brief history of the project. As I mentioned that we were conducting different types of monitoring using the different types of sensor platforms, using even satellite for quite some time. And of course, that morphed into unmanned aerial vehicle platforms and how that transformed into smart and connected systems at the present time. So this is a schematic which shows using Aster satellite, which we used for monitoring Aral Sea at the border of Uzbekistan and Kazakhstan. We monitored Aral Seas, as a matter of fact, the little Aral Sea and the big Aral Sea, and its transformation over a period of time going from 1985 to almost up to year 2000, where we monitored the Aral Sea. And as you could see in a time progression, how the sea literally shrunk in size, and of course we monitor different types of contaminants as well. This is a picture using MODIS Terra satellite, and using similar satellites we had monitored the environment, more specifically in the China Sea. As you could see, the clarity of water close to North Korea, South Korea, as compared to China, where of course lots of construction had been taking place. So this was part of the monitoring using different types of satellites, which we had conducted over a period of time. Also, there was a project in Thailand from a student of mine who had sensor networks, ground-based sensor networks, and using ground-based sensor network, we monitored pollution throughout Thailand to see over a period of time how the pollution increased and so forth. So as I mentioned, that different aspects of the monitoring we were conducting anyway, and of course this has morphed into the unmanned aerial vehicle platform at the present time, which I'll show you in slides. Also, NATO funded for us a project called Technical Advances to Monitor, Detect, and Remove Contaminants in Water for Safety and Security. And the purpose of the project was to assess, identify, and recommend different types of scientific breakthroughs in a multidisciplinary environment using international partnership network of research scientists to develop next generation solution that sense, detect, and remediate water contaminant so that we have a good water quality. And in doing so, we formed different types of, within the United States and outside the US, different subject matter experts, and we created different types of strategy for monitoring different types of contaminant, and of course recommending strategies. And one of the project was to develop a GPS, GIS-based contamination identification and level monitoring electronic display system, also called CILM-EDS, which is Smart and Connected System to monitor different types of contamination uh, using electronically, or a prototype to specially monitor contaminants and water level in event of natural catastrophe. This was simply to enhance situational awareness for the waterborne contaminants, and if there were a sudden increase in water level at wherever the sensors were located. So this is what the system looked like, that we had different sensors which were spatially located. All of them were connected to a central computer using cloud-based computation. So if either there are contaminants or there is some type of a water emergency, uh, there is a situational awareness in the sense that we would know, the entire nodes would know where exactly the emergency is, or the contamination level have exceeded a certain level. And we wanted to create different partners with this type of capability, and essentially to have a global network, uh, network of networks, so that we have a little bit more awareness of wherever there is a contamination. So this slide simply shows a schematic of one node, and of course there were 5 different nodes because there were 5 partners at that point. And this is what the system looked like, that we could monitor situation in Moldova, in the United States, and perhaps at the third partner location. And we had the capability to monitor all 5 partners at a given point in time, and also display that on a PDA, so that you have capability even though you're not in front of your monitors at a given point in time. You had the flexibility to monitor on a iPhone or a PDA at that point. And based on that, we made a rapid risk assessment verification research center, for online monitoring, water treatment, decontamination, water management type of a strategy. And of course, we used different types of decision support tools in conjunction with that to make policy recommendation to lawmakers. So obviously that was an outcome of that project point. So as I mentioned, that we were using all these platforms, and with the current technology, we were able to advance that. And one of the method which we used was using nanomaterials to advance the detection capability of the contaminants or different types of platform. We added nanomaterial based sensors. Although the time will not permit me to go into lots of sensors, I just wanted to very briefly introduce the concept of the nanomaterials, how that enhance the sensing and detection capability, and how that adds to these platform. So as you know, nanomaterials, these are, they have dimensions which are comparable with the fundamental physical quantities. And it is for that reason these materials provide some capability which are based on their reduced dimension. We can design material of our own choosing rather than being limited by the materials. So obviously it enhances the capability. And because of the fact they have dimensions which are comparable to lots of viruses and proteins and so forth. They also have biosensor capability, although the objective is to monitor the infrastructure, but I wanted to show the capability that these nanomaterial based platform do offer lots of additional capability as well. So this slide simply shows a generic schematic of different types of sensors on chip, network on chip, network-based optical integrated circuit, system on fiber. So we were able to make different types of platform, and some of them are integrated with the aerial vehicles so that they have enhanced detection capability. So most of my work in laboratory had been either fabrication of devices or risk characterization, which is simply the characterization of the materials and devices. So I'm going to show you some of that and transform that into UAV-based platforms. So I'm going to now very briefly discuss some of the UAV platforms, and the CARTS simply is commercial off-the-shelf capability which exists, which you can either buy directly, or if you have this advanced platform which I have shown, you could include this in UAVs to give lots of additional capabilities. So this is one of the platform which we developed. Of course, as you see in the underbelly, we could add different types of platform for ground-based monitoring. And this is what is proposed to monitor different types of activities for structural integrity, etc. So one of the device which is used, and of course now this is commercially available, extreme lightweight, so that you can add into the underbelly of a unmanned aerial vehicle, is LiDAR, which is light detection and ranging. This is a remote sensing method which is very widely used um, uh, and it uses a pulse laser to measure range, variable distances to the Earth. These light pulses combined with other data recorded by the airborne system, it generates a precise three-dimensional information about the shape and of course the surface characteristics. So this is very widely used in conjunction with the GPS, which gives us the precise location of the scanner. This slide simply shows different types of observations, and also three different types of LiDARs which are used. One is the ground-based, the other is the airborne LiDAR, which is one which I had shown you in this slide, which is the UAV-based, and of course spaceborne LiDAR, which I'm sure some of the satellites which we had used before had LiDAR capability, and that's the reason we could monitor different activities from the space, which I showed you before in my previous slides. There are two types of LiDAR. One is topographic and the other is bathymetric. The topographic LiDAR typically uses a near-infrared laser to map the land, while bathymetric LiDAR uses water-penetrating green light to also measure the seafloor and the riverbed elevation. These LiDAR systems allow examination of both the natural and man-made environment with accuracy, precision, and flexibility. And of course, you can capture all this data in a point cloud for different types of geospatial products, such as the digital elevation model, canopy models, building models, and contours. The next capability is called hyperspectral imaging, or also called chemical imaging, which is the combination of spectroscopy and digital imaging. Hyperspectral imaging is to obtain the spectrum for each pixel in the image of a scene with the purpose of finding objects, identifying materials, or detecting processes. Hyperspectral imaging devices are now commercially available and these are extremely lightweight, which you can integrate in a UAV-based platform. A special lens images the sample onto a slit of a transmission spectrograph. The spectrograph produces a spectrum imaged on a focal plane array detector, preserving the location of respective points on the slit and thus the points of the line on the sample. These successive lines on the sample measured over time form a complete hyperspectral dataset, also called hypercube, containing information in two spatial dimensions and also one spectral dimension. The hypercube is typically processed with similar hypercube measurement of a highly reflective white reference material and residual background signal. These results can be further processed, scaled, smoothed, and eventually compressed to produce information that can be used for measurement, such as composition, color, coordinates, and thickness. So this is a very useful device which can be integrated into this UAV platform. And this, of course, shows a commercial platform for monitoring different types of infrastructure. And of course, the specifications are given in here. As you could see, that these are roughly about 1.5 kilogram or 3.4 pounds, and they can be easily integrated into UAV-based platform. Then there are different types of imaging devices which are also integrated, called HD Zoom. It's a fully integrated high-performance electro-optical system. It's a 3-axis stabilization unit, and it can capture images up to 5 kilometers, 3.1 miles, with very high precision. And there are different other devices which can be also integrated into UAVs for different other types of application. And I'll show their applications for infrastructure types of monitoring. So the use of UAV in civil engineering are typically for surveying and mapping, for 2D orthophotos with composite imaging, for surveying drawing, orthomosaic maps, distance measurement, geographic information, also for 3D point cloud imaging, digital elevation, distance and volumetric measurements, building information modeling, and also for 3D imaging using LiDAR, as I had shown you before. By the way, these images I have captured from the web from various sources. These are not mine. This is only for demonstration of some of the capability of the UAV-based platform. Also, use of UAV in public infrastructure in the cases of bridges, dams, tunnels, highways, and more. It can monitor corrosion, roadbed wear and tear. As you could see, this is a mechanical system as compared to a UAV-based system. It not only monitors, but also can communicate with embedded platforms, embedded sensor network within the structure, as is shown in this slide, for different types of applications. Maybe a spillway cracks, may be geological site condition, hydrology, emergency preparedness, structural stability and viability, vegetation encroachment, etc. As mentioned, there are embedded sensor networks within the bridges and dams by which these types of UAV can communicate and, of course, can continue to monitor without actually bringing heavy equipment on those bridges. And of course, it can also measure environmental parameters using wireless sensor network platforms. Use of UAVs is also for the power grid, transport, and hydrology. Of course, this is very commonly used for railroad, for track alignment, track surface integrity, track wear and tear, bridge inspection, and of course, lots of other applications are shown. It's also used for power grid. There are different examples. And of course, again, for hydrology, again, there are lots and lots of examples. So as you could see, these UAV-based platform offer lots of capability for structural integrity and monitoring, obviously at a low cost and with a high. I would like to introduce laser-induced breakdown spectroscopy. This is a relatively new method because of the fact now it's available in a handheld type of a device, type of a format. This can be embedded with a UAV-based platform. And what it does is that it shoots a laser light onto a sample, and the light which is emitted is captured by a spectrometer, and you can then analyze this light to find the chemical composition of the sample. And the proposed use of this laser-induced breakdown spectroscopy is for environmental degradation of the infrastructures, different types of infrastructure. Of course, this slide shows different types of applications which are used using laser-induced breakdown spectroscopy, but it has lots of application for infrastructure types of. So this slide simply shows different types of platform which we have prepared using commercial off-the-shelf devices such as LiDAR, LIBS, hyperspectral imaging, and also some of the sensor platforms using nanomaterials which I have mentioned. So it provides an integrated capability to measure large number of parameters, ground-based parameters, which obviously can be used for different types of civil engineering platforms. So based on what I have shown in the previous slide of the unmanned aerial vehicles, different agencies have contacted us to provide different types of services, ranging from blizzard monitoring to chemical emergency, flood, droughts, hazmat incidents, and so forth. These devices, in conjunction with a ground-based communication relay resource management unit, it provides lots of capabilities, including earthquake, geological events, infrastructure monitoring, structural health monitoring, power outages, transportation, and so forth. So this slide simply shows in a broader context ecosystem of innovation using convergence of technology which are embedded into these UAV-based sensor platforms, and these convergence of technology provide enhanced situational awareness which we can obviously utilize for civil engineering types of applications. So in conclusion, I would like to point out that using paradigm shift, using nexus of technological innovation, we could use convergence of interdisciplinary fields to monitor structural integrity and structural health monitoring. These are smart and connected systems to provide enhanced situational awareness. Obviously, we have integrated new platforms, and of course, it creates new opportunities. Nonetheless, it definitely offers lots of challenges which we need to concurrently address, such as privacy and security. There is a crowded airspace, so you cannot use UAV every place you would like. Aviation versus UAV navigation, can they coexist? FAA does not think so, but definitely I'm sure there is a medium ground somewhere. Licensing requirement such as RPIC, which is remote pilot and control, bandwidth in terms of L3, G4, G5, battery versus weight lifetime, and so forth. So there are lots of challenges, but nonetheless, this is an innovative technology and it has tremendous application in civil engineering. So with that, let me conclude.